So let's look at one more situation, actually two more situations, and then we'll go ahead and call it wraps. Suppose a population of salmon reproduces at a rate of 25% per year. Fishing is allowed in the stream at a rate of R fish per year. If the stream is initially stocked with 500,000 salmon, how many fish can be caught so as to maintain a sustainable fish population? All right, so clearly we're modeling fish equals the number of salmon, and T is, we'll just say, again, time since we start the study, but we'll just go ahead and say time, and this is measured in years. So that already tells me that my model is going to have to be in units of salmon per year. Now, because there's a reproduction rate of 25% per year, another way we could think about this is that 25, every single fish in the population will on average produce 0.25 fish per, baby salmon per year. And I don't know if this is a valid figure. I've just created this. I'm sure if you were an ecologist and studying salmon, you'd know this figure better than I do. So let's draw our black box model. We know we have reproduction, which is causing the number of salmon in here, which is initially 500,000. So there are 500,000 salmon swimming in here, but we are putting more in via reproduction, and it's 25% per year. So that means that of the salmon, on average, that each of them will produce 0.25 baby salmon, which will now enter or be the inflow rate of our population. And this is going to be in new salmon per year. So that's the unit that I want. Now what I have coming out is just the fishing. Now we're not taking into account death or migration, etc. We're just saying that there are R salmon per year exiting this model. And therefore our dy dt is going to be the difference between those, which is 0.25y minus R. And you can see that we have that value of R right now that is we have that value of R in our model just like we did a different valued parameter in our previous problem. Now once again, if I write this as R is a constant, Y is my dependent variable, so the right-hand side only involves the dependent variable. If I write this as 1 times that, then I can think about this as my function of t, and I can think about this other one as my function of y, and so that means the equation is separable. So divide over 0.25y minus r. And I'm going to skip a step here to see if you believe me on this and just go ahead and verify that this integral will become this integral right here. And once I integrate this with Wolfram alpha, we can see that we get 4 natural log y minus 4r. So 4 ln y minus 4r. Again, if you had integrated this by hand, you may end up with a different answer. Wolfram alpha does some simplifications that make hopefully our lives a little bit easier. And now we multiply both sides by 0.25 or divide by 4, same thing. Natural log of y minus 4r equals 0.25t. And if we divide c by 4, that's still just an arbitrary constant. Exponentiate y minus 4r equals k e to the 0.25t. And add 4r, we get y equals k e to the 0.25t plus 4r. Now for our initial condition, we're going to put in 500,000 for the number of salmon at time 0. And so that's going to give us 500,000 equals k plus 4r. So that means k is going to equal 500,000 minus 4r. And our final model will be y equals k, which is 500,000 minus 4r, e to the 0.25t plus 4r. And now this is the number of salmon. This is the model for the number of salmon in our lake, our pond, excuse me, or wherever, stream, whatever it is we're talking about. So with that being said, we now can take a look at this for various values of r, and we want to determine how many fish can be caught so as to maintain a sustainable fish population. Well, we could probably agree that what that means is that we don't want the population to decline. So we want the population to either continue increasing or to flatten off. So let's go ahead and take a look at this in Desmos. So here we go. I've got that model in there. It's again asking me if I want to insert a slider for R, which I will go ahead and do. I'm going to go ahead and default that. I know that I can't fish fewer than 0. And maybe I'll just start off by going up to 500, and we'll see where that leads us. And then I might need to adjust that. So I'll click Done. And so we know that the number of fish initially is 500,000. So we're going to need our y-axis to go at least up to that. I'm going to go 600,000. There we go. And that allows me to zoom out. Now, if you're only fishing out one fish per year, clearly that's okay. We see that that population is going to explode based on the reproduction rate. And again, our assumptions in this model are only 2. That the salmon reproduce and that there's fishing. So nothing else. There's no disease. We're not accounting for anything like that because that's going to make our model instantly more complex. Now what I should see as I start to change this value of R is progressively that curve should kind of start to change or flatten. Now it's kind of hard to see because maybe with 500,000 fish initially present, even fishing 500 of them is probably not too big of a deal. So let me go up to 500,000 on that, because I know if I fished all of them out, then clearly they would die off very fast, right? Within just over the course of a year, because there's some reproduction going on. They last a little bit longer than a year, but not very long beyond a year. So as I decrease that rate of fishing, you can see that it takes, still the fish are going into extinction, but now it's taking a lot longer for that to happen. Now it's taking almost 2 years for them to go extinct. And eventually, you can see that this curve is starting to do something interesting. It flattens off. At 125,000 fish, nothing happens at all. That is, the rate at which we're fishing must be equal to the rate at which they're reproducing. So 25% of 500,000, if you think about it, is going to be 125,000. So if the rate at which they're reproducing is equal to the rate at which they're being fished, then obviously there's not going to be any change in the population. I would call this sustainable. That in other words, that if these are the only 2 things going on, fishing and reproduction, that you could fish 125,000 of them and still keep them intact. Now anything less than that would be desirable, right? Because 124,000 now not only allows you to fish at that rate, but also ensures that the population continues to grow. And depending on your ecological stance and what your objective is, you also don't want the population to become overpopulated. So in this case, the salmon population is going to blow up incredibly. But at 125,000, we are perfectly in good shape. And to wrap up this problem, we'll just say that by allowing fishing at a rate of 125,000 fish per year, the salmon population will remain stable at 500,000 salmon. So any fishing rate below 125,000, we're in good shape. And now we can even determine how many permits we need to issue, for example. So if we allow each fisherman a maximum of 10 salmon a year, then we could say, well, that would allow us to issue 125,000 salmon per year divided by 10 salmon per license. You'd be able to give out 12,500 permits for that particular stream. All right, we'll take a look at one more problem, and in the next lesson, we'll take a look at that 125,000 and how we could think about that 125,000 without having to go through this whole solution process, some other techniques in analyzing differential equations.